Yes, sir.
Okay. So today we discuss about Hamilton-Jacobi theory. We already know that from canonical transformation from a old set of coordinate to a new set of coordinate, it is canonical if Poisson bracket of new set of coordinate new QP Poisson bracket or Lagrange bracket will be equal to 1. Or another way is if P small p dq minus capital V dq is df, that means the exact difference. There are basically three ways commonly used to test whether transformation is canonical or not. And physically, canonical transformation means Hamilton's equation of motion remains invariant. The form of those equations will remain same in both set of coordinates. Okay. Hey, we already know about conservative systems. For conservative system means energy is a conserved quantity, and that energy is equal to Hamiltonian. Okay. Uh, okay. Uh, Non-conservative means Hamiltonian may not be equal to total energy. Okay. These are the variables we already know. Um, the canonical transformation may be used to provide a general procedure for solving mechanical problems. Mainly two methods are followed. Why we are using this transformation? Uh, why we are using in some problems polar coordinates than Cartesian coordinates? Also, in some problems, we choose particularly in electrodynamics, spherical harmonic problems, or spherical symmetry problems. We use spherical polar coordinates rather than Cartesian coordinates. Not in particular in electrodynamics, you use spherical polar coordinate instead of Cartesian coordinates. Sometimes we use polar coordinates instead of Cartesian coordinate. Why we use this transformation? Hello, hello. Am I audible?
Yes,
Yes,
sir.
sir.
Uh, So in some problems you use polar coordinates, spherical polar coordinates. Why? Because in those coordinates that particular problem can be easily solvable, isn't it? It is difficult to solve using Cartesian coordinates. So similarly here, we instead of small qpt we can use capital qpt. Why this? Because actually there are two important ways, you can say two kind of procedures. First kind, and the first approach, if the Hamiltonian is a conserved, then a solution could be obtained by transforming to a new canonical coordinates that are all cyclics. Okay. Hamiltonian procedure is suitable for cyclic coordinates. So if coordinates are cyclic, then it will be important to use the Hamiltonian procedure. And second approach is because why? So over there we have small qpt. If cyclic means one will be absent. Suppose Q1 is cyclic, Q1 does not appear in the Lagrangian, also in Hamiltonian. But in case of Hamiltonian, if Q1 is cyclic, then P1 is a conserved quantity because P1 dot is equal to 0. So P1 is a constant. Hamiltonian a function of QPT. So Q1 does not appear. P1 is a constant means P1 is no more a variable. So both Q1 and P1 uh, do not appear inside the Hamiltonian. One coordinate, one q, one p means two coordinate decreases. So now we have to solve with less number of coordinates. So for cyclic coordinates, Hamiltonian procedure is helpful. So when we transfer to QPT, we try to make some coordinates are cyclic. So suppose if in small QPT there are 10 number of coordinates, then it may be 8 or 6. So one way we reduce the number of coordinates. So in transformation, we want to make some coordinate cyclic. One way. Second way is a canonical transform the one coordinate to another new set of coordinate, so that which are which may be expressed in terms of initial values. we transform to new QP such that new capital Q, capital P will be some values, initial values of small q and small p. Let's say Q0, P0. Some constant value. We transform in such a way that new coordinates are constants. Then it is easy to solve. If there are constant, then only variability, other variable does not appear here. So in the second approach, it search a canonical transform from one set of coordinate to other, where a new set of coordinate, a new set of constant quantity, which may be the initial value of Q0, P0. So we transform from a variable small qp to a constant capital Q and constant capital P. Okay?
Yes, sir.
So that means transformation small q is a function of q0 p0 t. This q0 actually capital Q. This p0 is equal to capital P. Okay, we transform like this. This procedure is a more general one, and actually Hamilton-Jacob equation follows this procedure. So in Hamilton-Jacob equation, we get an equation. In this procedure, we first want to transform small qp to capital QPT through a canonical transformation. We know a canonical transform means form of Hamiltonian equation becomes remain invariant in new coordinate. So in new coordinate, if left Hamiltonian is k. In place of h, in new coordinate we take k. So according to Hamilton equation motion, qi dot is equal to del k by del pi. Pi dot is equal to minus del k by del qi. Okay, it is invariant. If k be the new Hamiltonian, then this is our relation. Setting k is equal to 0. If we set k is equal to 0, then what happens? Both q constant and p constant. K0 means derivative of 0, 0. This side 0. So q constant, we get new variable q and qi and pi are both constant in time. Again, k is related with the old coordinate by formula. K is equal to h plus df by dt. So for k is equal to 0 means h plus df by dt is equal to 0, or h plus d, h is a function of qpt, plus df by dt is equal to 0. It is convenient to f as a function of q, whole coordinate small qi and new coordinate pi. As you know, in general, actually we take f2. F2 is the common generating function because here the formula both positive. F2 means it is a form of small q, capital P, T. If you get the capital P from small q, our formula will be small pi is equal to a both positive del f2 by del qi. And similarly, capital Qi is del f2 by del capital Pi. Not it is the formula. So it is the common generating function. So only generating function is written, we take f2. So taking it as f2, f, we write is del f2 by del t. Because written here, small both are positive, small p capital Q. So putting the pi is equal to del f by del 2. So in place of here qpt, so capital Pi function of qpt. Okay. Is actually small p. But small p is equal to del f2 by del qi. So putting here we can write Hamiltonian is a function of small q1 to qn, capital, sorry, small p to Hamiltonian here, not f2. Small p1 to pn. So we can take p1 is this del f2 by del q1, p2 is del f2 by del q2, del f2 by del qn and t. So our Hamiltonian is a function of small q, small p, t. But in terms of f2, p can be written as, or pi can be written as del f2 by del qi. So in place of p, I write this. So that means If there are n coordinates q1 to qn, instead of p1 to pn, I write del f2 by del q1, del f2 by del q2, up to del f2 by qn. Okay. Okay. Hello.
Yes, sir.
Yes, sir.
Actually, this equation is known as Hamilton-Jacobi equation. Nothing new thing. Just know this is known as Hamilton equation. First, we said the Hamiltonian and Newtonian k is equal to 0. Why? If k is equal to 0, then nu p is constant, nu q is constant. Del k by del k, del k by del k, 0. Both are constant. So, okay. By setting k, but k is equal to h plus del f by del t. So, k 0 means h plus del f by del t is equal to 0. Okay. But f is your f2. H is a function of small q, small pt. But using f2, we have formula small pi is equal to del f2 by del qi. So putting this, I can write h function of q1 to qn del f2 by del q1 del f2 by del qn t plus d del f2 by del t is equal to 0. This is known as Hamilton-Jacobi equation. Here actually n plus 1 variables, n qn 1 t. So here n plus 1 variables. q1 to qn and t for the Taylor generative function. The solution f2 of equation 2 can be denoted by s and known as Hamilton's principal function. The solution of this equation is known as Hamilton's principal function, which is written as s. Mathematically have the form first order partial differential equation. So here first order partial differential equation. Solving it, we can find a solution f2, which is a function of q1 to qn, alpha to alpha n plus 1, and t. That alpha to alpha plus constants. They are related with del f2 by del q. Del f2 by del q1, del f2 by del q2. These are, we take is alpha. Okay. Where the quantity alpha n are n plus 1 independent constants. Why n plus 1? How we get this? Actually, when you get solution means in differential equation content. So we have to integrate. After integration, we get the result. In integration, we have a extra integration constant. So there are n constant for this differentiation plus 1 for additive constant. So n plus 1 constants. So solution known as complete solution of the first order partial differential equation. S itself does not appear in equation 2, only the partial derivative means f2 does not appear, partial derivative del f2 by del t. Okay. Or del f2 by del q1 or del f2 by del q2 appear. The partial derivative q or t are involved. And the S is some solution of the differential equation. Then S plus alpha, where alpha is any constant, must be also solution. If S is a solution of this equation, then if you add alpha constant, because if you take derivative del f by del t 0, so it is also a solution. If one of n plus 1 constant of integration in equation 3, therefore must appear only as the additive constant. Among the n plus 1 constant, one is additive constant. So there are only n constants, n alphas. Since fraction function in the transform equation, and the complete solution we can like this. So we neglect that additive constant alpha n plus 1. So S is basically function of q1 to qn, alpha 1 to alpha n, and t. When none of the n independent constant is only additive, now S must exactly match with the desired form of f2. So S is nothing but the desired form of f2. So this equation represents S as a function of n coordinates and time. N independent quantity alpha I, we can take n constant of integration to new momenta. So alpha is basically our momenta pi. Because in place of pi we written Hamiltonian is function of qpt. So in place of p, actually alpha is written. But from our analysis we know pi is equal to del f2 by del ki, or setting f2 is equal to s. Hamilton's principal function del S by del Qi. Where S is a function of Q alpha t, and capital Q I will del F2 by del Pi. So F in place of F2 write S, in Pi write alpha, we found del S by del alpha I, which is another constant beta I, because our aim is to get alpha I constant, sorry, Qi constant, Pi constant. Qi is beta I, Pi is alpha I. Okay. The constant value of Qi is known as beta I, constant value of Pi is known as alpha I. This constant with the initial condition. Okay. Del S by alpha I at t is initial condition, you know that initial condition. So we found Qi. Now our Qi is function of alpha beta t. Similarly, Pi is a function of alpha beta t. Okay. Alpha means capital Qi, beta means capital. Sorry, alpha is capital Pi, beta is capital Qi. We got it, yeah? Alpha is capital Pi, beta is capital Qi. So this is a transformation. This is the desired complete solution of Hamilton's equation also. This is actually procedure of Hamilton-Jacobi theory. Very simple procedure. We know that we have to transform a new coordinate which is constant. That means capital Q constant, capital B constant. Making that constant, we have to set k is equal to 0. Putting k is equal to 0 and using the relation between new and old Hamiltonian, we found S plus df by dt is 0. H is a function of small q pt, F2 is a function of small q capital Pt. Now, we know that small p is nothing but del F2 by del q. So, instead of small p, we have write to del F2 by del q. But small p del F2 by del q. So integrating it, we found actually n constants here and one for additive constant. Their constants are named as alpha. But comparing it with the actually it is written in place of small p. So p is alpha I. Again, setting that we found qi is equal to beta I. So we go from old set to new constant set of transformation. This is your aim. Okay? Hello?
Yes, sir.
Sir.
Sometimes I for the physical significance of this Hamilton's principal function. So if you take derivative, you can see some quantity. So now let's ds by dt. S is a function of q alpha t. Take it derivative. Taking derivative del s by del. Apply this rule. If f is a function of x y z, df is equal to del f by del x dx, del f by del y dy, del f by del z dz. Similarly, del s ds by dt is equal to del s by del qi dqi by dt, or del s by del alpha by del t. Okay, ds by del t. So del s by del qi, dqi by dt means qi dot, and alpha is a constant, derivative is 0, or ds by dt. So again, pi is equal to del f2 by s is f2, del f2 by del qi, so putting it py qi dot plus ds by dt. But since we have s plus df by dt 0, del f2 by del t is equal to minus h, which is same as del s by del t. So ds, so del s by del t, you can write here minus h. So ds by dt is equal to sum of pi q dot minus h. But this quantity is your Lagrangian. We already know that. So ds by dt is Lagrangian. So you can say s is equal to integration of L dt plus constant. So the Hamilton's principal function differs as much from the indefinite time integral of the Lagrangian only by a constant. It is nothing but integration action. Only differ through a constant. Okay. So Hamilton's principal function nothing but action. Integration of L dt with the additive constant. When Hamiltonian does not depend explicitly on time, then Hamilton's principal function, if a Hamiltonian does not depend on time, its time is absent, then this Hamilton's principal function can be written as actually it is a function of q alpha t. If main function does not contain time, we have to extract time from that. So I write like this, minus alpha t here, separate from w q alpha. At that time, WQ alpha is called the Hamilton's characteristic function. Okay. So, what is the physical signal W? Similarly, calculate dW by W is a function of Q alpha. dW by dt is equal to del W by del Qi into dQi by d dot and Qi dot. Again, del alpha by del T, which is 0. But Pi is equal to del S by del Qi, putting this del W by del Qi. So, this is nothing but Pi. So, Pi Qi dot dW by dt is equal to Pi Qi dot. So, W Pi Qi dot dt integration. Pi dq by dt integration. So cancelling this, you can write integration of pi dqi. W is which is called abbreviated action p dq. Okay. This is a procedure very important is general solve the Hamilton harmonic oscillator problem using Hamilton-Jacobi method. Okay. Because for the harmonic oscillator very simple one, it is used to actually when you study the black body radiation. The cavity is considered as filled with harmonic oscillators. Similarly, when you study the crystal lattice, you assume that lattice has harmonic oscillator and got the Debye and then Einstein equations. Okay. So basically, in theory, we use harmonic oscillator as the base point, both in classical mechanics and quantum mechanics. Okay. So we know Hamiltonian for a harmonic oscillator is kinetic energy p square by 2m plus potential energy half k cube square. We already do it in Lagrangian formulation. Or if putting omega is by m root over, it equal to m omega square q square. For conservative system, h is equal to e. Now Hamilton-Jacobi equation we can get by setting where p is equal to dLs by del q. Okay. We have the equation Hamiltonian p square by 2m plus half k means half m omega square q square. Now slightly rearrange it. We know this p is equal to del s by del q. Put it and then multiply 1 omega and divide 1 omega. So it will be m square omega square q square 2m. Okay, 1 by 2m taking common. Del s by del q whole square plus m square omega square q square. Okay. But h is equal to h plus df by dt 0 del s by del t 0. So del s is equal to f. So h is equal to minus del s by del t. So h in place right minus del s by del t is this. So common equation is adding this one equation, Hamiltonian equation. This is the equation which is s q del s by del q and del s by del theta. Hamilton-Jacobi equation. We need is solution. So solution means take S is the solution which can be written as WQ alpha minus alpha T. Okay. Now use this there. In place of S write W minus alpha T. Or del S by del Q alpha T alpha constant T constant with respect to Q so 0. But here del S by del T is minus alpha. So put those minus alpha here only del W by del Q square. So we got this equation where del W by del Q square is equal to this 2m alpha minus n square alpha. So del W by del Q is this root over W is equal to integration of dq. Integrating it, we found W square root of 2m alpha taking outside this. But by definition, S is equal to WQ alpha minus alpha T. So S is equal to this W minus alpha T. So we can integrate equation this minus alpha T, putting beta is equal to del S by del alpha. So we can write del Q. This is actually del S by del alpha. This quantity. Putting we found m dq by t or beta is equal to this, or taking t in this side, b plus beta plus t is equal to this. And we have to integrate it. For the integrating it, we have to take the x dx this, then a normal form integration give you sin inverse x means sin inverse m square by 12 root over q. So sin omega beta plus t is equal to this. So that q is equal to 2 alpha m square root over sin omega. Okay? Hello?
Yes, sir.
Yes, sir.
Yes, sir.
There is a problem in derivation. It is a very important question. Sometimes ask solve it. Just normal integration. If you assumptions, see simple things. Okay. So we found actually q. Okay. Then we can calculate p. P is equal to del s by del q. Taking this del by del q, we calculate the p. So know p and q. So you can find the Hamiltonian. Oh. Okay, also P is equal to mq dot. You check whether P Q P is moment of mass into velocity. Q is position coordinate. So you check also if Q no, you can also calculate by mq dot. Okay. Taking beta is a constant, so multiplying omega beta prime another constant. We can equation can be written like this. Then on it we have already got the solutions. Now to complete the procedure, alpha beta must be connected with the initial condition small q0 and small p0 at time. Uh, since any p square is equal to 2m minus m omega square q square alpha. Okay. Equation 8, you write this equation. See this equation. Then p square by 2m, q is given, p is given. This one p. Is alpha. 8. That is equation 8. P square 2 from m square. Squaring it. This is actually equation 8. I have forget to written. Now square this quantity. What do you find? P square is equal to square root over, okay, 2m alpha minus m omega square q square. If you take the initial condition, then p will be p0, q is equal to p0. So 2m alpha is equal to this. Again Hamiltonian is equal to minus del s by del t. And we know with Hamilton alpha, so taking derivative alpha. So alpha represents total energy or total Hamiltonian of the system. So 2m is equal to p0 square plus m square. Okay. So alpha is equal to this, or you can h. Alpha is 1 by 2m p square by m square. So from this you can also say Lagrangian sum of p q dot minus h. You get this. Or aiming to getting the solution, this is fine. QP form, and if you add this, you can add this value. Okay. This is actually procedure of Hamilton-Jacobi theory. So how L calculated? Okay. Then also you calculate a S similar formula, and finally we show that the condition S is equal to integration of L dt plus constant. Oh. So this is the procedure of Hamilton-Jacobi theory. Okay. There are few problems. If the Hamiltonian is independent of time explicitly, so that it is a constant and equal to total energy. Hamilton does not contain time. So H is a function of only QP, and we know H formula Pj Qj dot minus L. So dH is equal to dPj Qj dot plus Pj dQj dot minus dL. In place of L, L is a function of QP. And del L by del Qj dQj, del L by del Qj dot dQj dot. Putting all, we found dl this, so dh will be this quantity. But dh by dt, if taking derivative, it will dpj by dt means pj dot qj dot and pj dot qj dot which is 0. So h is a constant. Again h is 2t minus l is equal to t plus b. Very simple to prove this. Another question from the last class. So that this transformation is canonical. Using Poisson or Lagrange bracket, we cannot check it. we have to use this exact differential. P dq minus capital P dq is equal to dq, where capital PQ is given. So if you small p dq take, then capital P is here dq. Taking differentiation tan inverse q by p, 1 by 1 plus q square p square, p dq minus q dp by p square. Okay. So it is will be p square plus q square, and numerator p square q square cancel, numerator will be p square, and that p square will be cancelled with this. So it is nothing but half p dq minus q dp. Taking half p dq plus half q dp, a differentiation of half q. So it is transformation is canonical. Okay, are you getting my point?
Yes, sir.
Yes, sir.
This is all about Hamilton-Jacobi theory, and we take one example. Particularly, example asked in your examination because your questions are problematic questions. Then they don't ask theory, derivation of anything. They actually put questions and problem how to solve this harmonic oscillator using Hamilton-Jacobi theory. So it is one of the important questions. Next one is action angle variable. Before going to that, we have to know some about periodic motion. Okay, you already know in our plus 2 plus 3 what is the periodic motion.
Sir, କୋଉଟା
Uh,
important question କହିଲେ?
um, Harmonic oscillator problem using Hamilton-Jacobi theory.
Okay, sir.
Okay. We go to periodic motion. You already know periodic motion means
Time period same ରହୁଥିବ
the motion
motion
which
ଗୋଟେ
repeats
constant time
itself
period.
after a regular interval of time. The motion which repeats itself after a regular interval of time. Okay. So if you plot, actually there are two kind of plot. The motion plot. Okay. Uh, you see, if you this plot with the angle 0 to 2 pi, then the motion repeats itself. Sin x cos x the wave. Sin x repeats itself. What is the value of 0? Then 2 pi. That repeats itself. One kind of thing that is known as rotation. Another kind of thing, uh, okay, where actually motion repeats itself in this pattern. That is known as libration. That is called libration. Okay. You have to write them. So periodic systems are those which repeat their state of motion after a constant interval of time, known as period or time period. In the phase space means QP space. One axis, this is Q axis, this is P axis. All such periodic systems need not retrace their path. All need not retrace means all are repeat motion like this path. Some have this type of path. What I see, it is also periodic motion. It is sine wave, is a periodic motion. But sine wave is not like this repeat motion. In repeat motion, but structure is like this. Okay. Paths are not need not retrace their paths. Which retrace their paths, which retrace their path in phase space are called liberating system. And the type of motion is known as libration. Okay. In their motion, both Q and P are periodic functions of time. In libration, both Q and P are periodic functions of time. With the same frequency, periodic motion of this nature will be found when the initial position of point lies between two zeros. Actually, what we know in central pulse motion, its motion in this like means circular means there must be two turning points, but it changes the direction of motion. Okay. The same frequency motion nature will be found when the initial position of the lies between two zeros of the so initial position here start or anywhere lies between two zeros, two turning point. Two turning point means where total energy is potential kinetic energy is zero. This line means two turning points. Zeros of the kinetic energy means turning points. So that motion is known as libration. Okay. Not rotation. Rotation, phase space diagram, rotation is like wave, sine cos wave. Phase space diagram of libration is like a loop. Remember, since QP returns to the original transient values in one period, the system point retraces steps in every period and the orbit in phase space is closed. This motion is characteristic of common oscillatory system. One time a harmonic oscillator also in Hamilton Jacobi theory, you find QP both are function of sine and cos. So if you periodic motion, Q square P square, then R equal 1. So Q square P square, if you add ellipse, suppose harmonic oscillator, equation is P square by 2m plus half KQ square or m omega square Q square is equal to Hamiltonian or energy. So you can write P square by 2m divide E in each term, 2m E plus Q square by 2e divide K is numerator, I can take 1 by K is denominator, so 2e by K is equal to how much? 1. This equation can be written like this or not? Hello?
Yes,
Yes,
sir.
sir.
But this equation is equation of what? X square by a square plus y square by b square is equal to 1. This is equation of, let's say it is 2m root 2m square. X square by a square plus y square by b square is equal to 1. It is equation of ellipse. Isn't it? Hello?
Yes, sir.
So if you plot, take x is equal to q, y is equal to p, so obviously it is the ellipse. Ellipse is closed path. So phase space diagram of harmonic oscillator is closed path. So harmonic oscillator phase is known as libration. Okay. In the other kind of periodic motion, Q itself is not periodic, but it shows that when Q is increased by some value, say Q0, then configuration of the system remains essentially unchanged. Okay, just like sine theta, it contains sine theta. So sine theta means sine wave does not repeat like this behavior. What is the value of 0? If you add 2 pi, sine 2 pi that, sine x, sine 2 pi plus x is that. Okay. That is called rotation. It is because always associated angle theta. Angle is 2 pi, angle is 2 pi plus x. So increasing q by 2 pi, then there is no essential change of the state. So the position coordinate in this space, periodicity. Okay. So that is called rotation. So this is the picture of libration. This one is libration. This one is rotation. Clear? Hello?
Yes, sir.
Or both
Yes,
are
sir.
periodic.
Yes, sir.
I think even the suppose simple pendulum, we have to solve it problem. Consider the simple pendulum. Simple pendulum we will solve. Its kinetic energy half ml square theta dot square, potential is mgl 1 minus cos theta. So it Hamiltonian will be, if you take some pj qj dot minus l, it will be p theta square plus 2m square. Also we know Lagrangian is equal to t minus v. Hamiltonian is equal to, for a conservative system, Hamiltonian is equal to t plus v. So if t minus v given, only we change the minus and plus, then we got the this. But in Hamiltonian, you have to replace all q dot by p. Hamiltonian is a function of p and q. Okay, there is no q dot. So convert it theta dot L by L p theta. We got this. This is the Hamiltonian. Or you can calculate as is equal to sum over p q dot minus L. In that way, you can also Lagrangian Hamiltonian. Hamiltonian is basically represents the total energy. The total energy is this. If you take mgl is completely constant, then total energy is in terms of variable like this. Okay. So p theta square by 2ml square e plus mgl cos theta, or p theta plus minus root over of this. So we have three cases from here. One case E greater than MGL, E less than MGL, E is equal to MGL. Then what happens in three cases? If you see, but E less than MGL. See this? E is less than MGL. Again, we know that cos theta value is -1 to +1. What is the value of cos theta? Cos theta. So compare this. Okay. E plus MGL cos theta. The periodic motion only occur, but it is periodic motion. If theta dot less than theta prime, getting by the equation this cos theta is equal to minus E plus MGL. Under this condition, the pendulum oscillates between minus theta prime to theta prime. Cos theta minimum value -1, maximum value +1. So what cos theta E plus MGL cos theta, setting it actually 0 momentum, we get the cos theta. So this is the picture. We can solve it in simpler way. I don't go into that. It is another E greater than MGL. It is not needed actually, not our syllabus. Then E don't go there. Okay. We have to find the phase space diagram of a simple pendulum. How we do it? For that, the procedure is uh, written here. Come to here. Leave this. We can set the how we get the diagram. Okay. It is the exact diagram, but it is not our syllabus. We have to only sometimes ask the write the phase space diagram. We start from here. And equilibrium, we already discussed that two kind of equilibrium: stable equilibrium and unstable equilibrium. For stable equilibrium, potential energy is minimum. Unstable equilibrium, potential energy is maximum. How you check potential energy minimum? Equilibrium, it is stationary means first we check equilibrium means force is equal to 0 or del V by del X is equal to 0. Second thing, if second derivative is less than 0, then it is large maximum. So it is unstable. If second derivative is greater than 0, then it is minimum. Stable equilibrium. Okay. So stable equilibrium point, if in phase space, is actually the origin. If you get for a system stable equilibrium point, it behaves like a origin. Origin means around it is always this circular path or elliptical path. Stable equilibrium point. Unstable equilibrium point always behaves as a bifurcating point. If this is an unstable equilibrium point, then it is a bifurcation, phase space bifurcation occurs. Okay. So in this way, you can check the diagram of phase space. Okay. So stable equilibrium, unstable equilibrium. Uh, we already did this problem. In phase space, it is important, very, very important. Stable equilibrium point acts as origin, and unstable equilibrium point acts as a saddle point. Saddle point means where bifurcation occurs. The two paths of constant energy in phase space interact at saddle point. Two, uh, in other words, at saddle point, bifurcation of the path occurs. Bifurcation occurs. Okay. Uh, so here, if you take this first calculate Lagrangian, we already know the Lagrangian. This one. What is the Lagrangian? We have written where? This is half ml square theta dot minus mgl 1 minus cos theta. From that, you calculate what is V, potential energy. This is your potential energy, mgl 1 minus cos theta. mgl 1 minus cos theta. Find equilibrium point, take a derivative and set it 0. If you take derivative, it will be how much? The derivative 0, second term minus mgl cos theta. Cos theta means derivative minus sin theta. So sin theta mgl sin theta. So at equilibrium mgl sin theta is 0. That means sin theta 0. So theta will be how much? Hello?
0.
Only 0 or 2 and pi? Hello? 0, 2 pi, 4 pi, minus 2 pi. In trigonometry in high school, you know that when sin theta is equal to theta is equal to
9 inverse 2.
uh, n pi. Not 1 pi, n pi. N pi. And sin pi is how much? Sin pi is sin 100 degree?
0.
0.
Zero.
N pi is 0. No, if n pi is 0, then theta is equal to n pi, sin theta 0. So each pi there is a origin. Then sorry, n pi 0 means equilibrium point. N pi is the equilibrium point. Now check the equilibrium point. When theta is equal to 0, what is the value of this second derivative? Its second derivative will mgl sin the right derivative mgl cos theta. Theta is equal to 0. Cos theta is equal to how much? 1. So it is mgl greater than 0. So it is a stable equilibrium point. Theta suppose plus pi or minus pi. Cos pi, cos of x is equal to cos of minus x. Same. Cos pi or minus pi. Value will be cos pi is how much?
1.
Cos pi 1 or minus 1. Sin pi. Cos 0 1. Cos pi 1 or minus 1? Hello?
-1. -1.
Minus 1.
Minus 1.
So
Minus
minus 1 means it is minus mgl. Less than 0. So it is a unstable equilibrium point. So look at the figure. So these are pi point means unstable equilibrium point where bifurcation path occurs. This is stable equilibrium point or origin. It behaves as a origin. It is for different energy levels. This is for different energy. Actually, in your not a class exam, if you appear net or get this type of problem generally comes. A given potential is given and some options are given, which is its phase space trajectory. In that case, you use this formula. You take its first derivative, equate it 0, find stable equilibrium, unstable equilibrium point. Stable equilibrium point is like waves as a origin, unstable is a bifurcation point. Okay. Actually, this is the written here. Uh, Not written in syllabus, but this is the rule. No? There are other some rules. The main rule, simple harmonic oscillator. Also, you can check potential is half kx square. The plot is potential energy and energy. Take its energy. Whatever be the energy, you see there are two turning points. That means motion is bounded. For a simple harmonic oscillator, motion you always write it is a ellipse, ellipse, energy increases another ellipse. If energy increases another ellipse, from potential also you can plot this. Uh, okay. That's the simple harmonic oscillator. Another question is a perfectly elastic ball bouncing normally between 2 points. Yeah, suppose a ball is bouncing between 2 points. What will the phase trajectory? What will the trajectory? When coming with a constant momentum p and strikes here, again go back opposite direction. Let's say momentum is negative. So this is its trajectory. It comes here and strikes here. At that point, it changes momentum. Its negative value. Okay, this is we solve the simple harmonic oscillator. Why told it? Localizing this. Okay. There are also few diagram functions about v is half x minus half x square plus 1 by 4 x4. If you plot, this will look like this. So how you draw it? First you check its equilibrium point, then which is stable or unstable. So +1 is greater than 0 means stable. 0 is unstable point. So 0 there is a bifurcation. How you plot is direct potential is level like this. Okay. And these are actually these are not written in your syllabus. It is for what this type of problem comes in net CAT exam. So I am discussing that because they are related with this field. Okay, but your syllabus it is an action angle variable. Come to that quickly. Action angle variable. For periodic motion, both libration and rotation. Libration means when phase space trajectory is closed. Rotation means wave. We can introduce a new coordinate J designed to replace the transform constant momentum alpha. This variable is known as action variable. We already know in Hamilton's principle that calls integration of LDT A is known as action variable. Okay. ALDT, what is the dimension of ALDT? If you check, it has same PDQ. Because suppose area in the harmonic oscillation, how you calculate? This is P axis, this is Q axis. What is the area? Area bounded between these two PDQ integration. Okay. So this is actually area, which is known as action variable because it term LDT has same dimension action with PDQ. So we call J close because here periodic motion. So integration of a closed path PDQ is known as action. But the integration to be carried over a complete period. If it is a libration, it is a period angle particularly sorry libration. It is a complete path. For a rotation, it is angle 0 to 2 pi. Okay. J always have the dimension of angular momentum. For Hamilton Jacobi theory, we have a relation like this: S is equal to W cube alpha t. So H and H is equal to minus del S by del T alpha. P del S by del Q del O del Q. We already know in our first slide we discussed it. So let define J. P dq P J del W by del Q. Q. So P is a function of Q alpha. H is equal to alpha. We know Hamilton is alpha. Alpha is equal to P square by 2m plus half k Q square. So from that, suppose H is equal to alpha. So actually alpha is a function of P square by 2m plus half k Q square. Reversing it, I can say P is a function of Q1 alpha because other are constant only. If I write P square by 2m is equal to this minus alpha, so I can say P is a function of Q alpha. Okay, that is thing. So H is a Q of alpha, P is a function of Q alpha. But J is a function of QP integration P integration will over dq. So dq will be integrated and in place of q limit will put. Only variable is p. So j is a function of p, but p is a function of q alpha, and q will be integrated here. So only variable is alpha. So we can write j is a function of alpha only. Clear? Hello?
Yes, sir.
Yes, sir.
Yes,
J
sir.
is a function of alpha only. But alpha is equal to h, so you can say j is a function of h or h is a function of j. This is the starting point. So Hamilton's characteristic function we know W is a function of QH, now it is related to QJ or Q alpha, it becomes QJ. Alpha is the generalized coordinate conjugate to J known as angle variable. J is generally a momentum type thing. The coordinate correspond to it known as angle variable. For that reason it is called action angle variable. Angle omega and omega can be calculated theta p theta relation theta theta del h by del theta dot del h by del p theta and angular velocity omega del h by del p theta or omega is equal to del w by del j. Now the equation of motion for the angular velocity q dot is equal to del h by del p becomes w dot is equal to del h j by del j, which is nu. So omega is equal to integration of nu t dt, or omega is equal to nu t plus beta. Now the change in omega as q goes through a complete cycle. Q goes through complete cycle here, or q goes through complete cycle here. The omega varies from over a cycle. So del w by del q dq. So del omega change will be del w by del q into dq over complete cycle. Del omega is equal to del w by del j. Substituent is only small w means omega, capital W is w character Hamiltonian characteristic function. Putting that, we found take it in double derivative del square w by del q del j. So del w is integration of this, but integration is over dq, so you can take del outside. So integration of this quantity, but del w by del q is p, so it is integration of p dq. But p dq is equal to j action, so del j by del j it will be 1. So the omega changes by unity as q goes through a complete period. Okay, that's change. So then from that we can calculate what omega is frequency into time period, which is equal to 1. So frequency is 1 by tau. No, it plus 2. So nu is therefore known as frequency and with the periodic motion q. Okay, if a system 1 degree of freedom, it is periodic, then the frequency can be calculated. W dot is equal to del h by del j, which is equal to nu. So nu is equal to del h by del j. The formula frequency nu is equal to del h by del j. Sometimes asked in the examination, harmonic oscillator using action angle. Similarly, your harmonic oscillator is important. Your Lagrangian or even Hamiltonian. Then J is equal to action angle integration of P dq. From this you can calculate P is equal to this 2mh, H is equal to alpha in our theory. So it is equal to this 2 alpha minus m square m square. From this you can calculate substituting here Q is equal to 2 alpha by m square. Or P is equal to m q dot. Is not it? So you can calculate the q dot p by m, integrating it, you will get a q. Or from substituting this equation, you can calculate q. H is equal to alpha. So substituting value of p here, you can find q in terms of p and alpha. Two ways are available. So j is equal to complete period means 0 to 2 pi, integrate it. This integration p dq, p dq given, p given, t, q given, so tq. So finally integrating, we found j is equal to 2 alpha pi by omega for a harmonic oscillator. So j is equal to alpha is h, 2h pi by omega. So h is equal to j omega by 2 pi. Alpha is equal to j omega by 2 pi. But nu is equal to del h by del j. So nu or omega by 2 pi, whatever may be, you can calculate equal to 2 by 1 by 2 pi k by m root over. You know. It is some problem. One dimensional Vx is given, you have to calculate new time period. Okay. E new. So J is given, J formula is this P dx, P dq. If it is ellipse, so you know area of a ellipse is equal to pi AB, pi semi major axis and semi minor axis. Okay. Or if axis is your PQ, Here integration gives you PQ, pi PQ. Constant doesn't matter, but P and Q. For P value is how much? A. What is A? Written P square by 2me. What you written there? The square. I have written plus Q square by. From energy equation, I got this equation. I have written somewhere last. Where? First. You have written that. Yes, yes. That equation is very important here. Second side. Okay. Hamiltonian or energy E is equal to P square by 2m plus half kq square. Isn't it? It is represent an ellipse because dividing E P square by 2me kq square by 2ek this or 2me root over square which is a b and 2 root over square which is a x square by a square plus y square by b square is equal to 1 and ellipse. So x axis q. So a is proportional to e to the power half, whatever be the constant you will take. Similarly, b proportional to e to the power half. For square case, here actually see potential is a x to the power 6. That case x square half k x square, half k is constant, a x square for a harmonic oscillator. So we write 1 by 2. So here 6 means 1 by 6. So here both component. Okay. Kinetic energy is same, p square by 2m. So kinetic energy remains e to the half a, but b will be potential energy part. This one here 6. So taking it by 1, we have to write 1 by 6. Okay. Also to you can say how it is vary total time period. Where is this? No. Okay, everywhere there is, see. Here given 4. So B proportional to 1 by 4. A proportional to 1 by okay half. But here you 1 by 4. So you multiply this, get the result. So here x to the power 2n means 1 by 2n. Okay. For time period formula you have to remember del j by del h. And j is equal to integration of p dq means pi ab. Okay? Hello? Hello?
Yes, sir.
This
Yes,
is the
sir.
formula you have to remember for time period. T is equal to del j by del h and our j is equal to integration of p w action angle. If you solve it pi ab. The potential is x square x4 x to the power 2n. There's not that type of question. So you can count this. If you check, you can. Okay, all about this theory, then we rigid body dynamics and only one two things Liouville's theorem like you want to are missing from this unit. We'll discuss in the next class Monday. Okay.
Yes, sir.
Okay.
Sir, Monday is your last class or what?
No. I'll take
Okay, sir.
2-3 classes. Okay. Because there are
Yes, sir. Sir, on the last class of MPH-6, will you provide some important question on this?
okay. I will take 3-4 classes more.
Yes, sir.
Okay. Okay, I am leaving.
Yes,
Thank you.
sir.
Thank you.
Thank you, sir.
Thank you, sir.